Hi, and welcome to our next in a series of videos on modeling, SysML, and UML. I'm Jeff Cohen, and I'm with 321 Gang, and I'm a systems engineering specialist and a modeling specialist. In this video, we're going to be covering SysML. This, as you can see, is the third video in this series. And this one, as I said, is targeted more toward the systems engineers because we're going to give a brief overview of the SysML diagrams. However, if you are a software person, stay tuned. Watch this video because you'll understand a little bit more about how your systems colleagues work. By the same token, if you're a systems person, watch the other video on UML. So you'll understand what the software folk are expecting and what they're going to be dealing with. Let's start by stepping all the way back before we get into what the diagrams are and talk about what we're trying to do. So let's start by saying, well, what is systems engineering? It's a little bit unique among the engineering disciplines because first of all, we're cross-discipline, and second of all, we don't make products. We don't cut the code, we don't make the boards that get spun, we don't build the drawings from which they build big structures. Rather, we get paid to think. Think about what the product is going to be, or what the project is going to be, and how it's going to be all brought together. Like I said, we don't produce the software or the hardware or the mechanical. We produce the specification. In other words, we say, what has to be done, what the parts are, and what parts are going to do what, and what the goodness is for the validation for the testing. That being said, I tried to take a typical workflow and realized that each of these swim lanes here could be a different person or just the same person wearing different hats. We typically see within the engineering, the systems engineering community, people who specialize in requirements engineering, systems engineering, and then the subsystems engineering. In the requirements engineering, we're the guys who get the initial statement of work from the customer, the initial customer requirements, and turn them into things that can be used. For groups that aren't getting requirements from the customer, but are rather getting functions and features that are going to go into a product, we're going to do the same thing. We're going to get that feature list, that function list, and we're going to turn those into requirements. So we're going to take whatever that documentation is, we're going to import the requirements into a requirements management tool, then do some analysis on those requirements because they're never quite right from the customer. There may be more than one comment, there may be more than one thought, it may not be a complete or testable requirement. We're going to turn those requirements into things that meet the 5 C's. I've got another video on how to do requirements management, and that's coming up later in the series. Finally, we'll export those requirements into the modeling tool. Now, the systems engineer is going to take those requirements and identify the major capabilities of the system, or if it's a subsystem engineer, the parts of the subsystem that they're looking at. We're going to derive any additional requirements, refine those use cases that captured that features and functionality, refine them to be more specific, then allocate that functionality to the parts of the system. And finally, we're going to define the interfaces. Similar, you can read down the subsystem engineer, pretty obvious things. Now, I've said in the last 2 videos, and I'm going to say it multiple times again, this is not necessarily a waterfall. As a matter of fact, I'd be very surprised if you were doing it in a waterfall. Each of these lists of tasks, if you will, the little actions that the engineer will perform in the swim lane, well, those can be done in parallel. As a matter of fact, I would expect those to be done on 2-week intervals, a sprint, and at the end of the 2 weeks, the transition goes over to pass it over to the next group. So if we're going to do requirements and the model, it helps if we have a common language so that when I draw something a certain way, you look at it and you know exactly what it means. Well, that's the purpose of the SysML. And this comes right out of the OMG's What is SysML? SysML is a general purpose graphical modeling language, emphasis on language, for specifying, analyzing, designing, and verifying complex systems that may include hardware, software, information, personnel, procedures, and facilities, and we can go on from there. The first thing to notice that this is a standard, and it's a standard that's maintained by the Object Management Group, the OMG. SysML is supported by many different tools. It's not owned by any one vendor. As a matter of fact, it's owned by the OMG. And we see excellent acceptance in a lot of different industries. The big ones that I see: aerospace and defense, transportation, oil and gas, and medical. Notice that all of these are highly regulated, things that need to have very good documentation to know where their decisions were made and why they were made, because things do go bad and you need to go back. I've also seen SysML used pretty effectively in the material handling and in the electronics group, especially when the product doesn't live just in one chip or just on one board, and it has to interface to a lot of different things. SysML is great for doing that allocation among different parts and defining what the parts of the system need to be. Now, this diagram comes right out of the spec. And what it shows is that basically SysML has three types of diagrams. It's got requirements diagrams to say, what is the system going to do? It has structural diagrams to say, what are the parts of the system and how do those parts interact? What are the relationships and the interfaces between those parts? And there are behavioral diagrams. Behavioral diagrams that say, given these interactions, what is the part supposed to do? Or given this larger picture, a function or something like that, a feature of the system, what does that feature mean to us? How do we go about solving that solution uniquely, that even though lots of us get the SOW, this is our specific solution? Let's start right away with a requirements diagram, because most of the time you'll actually have requirements or some idea of where you're going to be. Even if you're just getting features and functions, you may start with a use case diagram, but you'll probably go back to a requirements. So the purpose of the requirements diagram is to keep the requirements within the scope of the model that you're building. Don't have all the requirements for every dot and tittle if you're only looking at one subsystem of the overall system. We use the diagram because it makes things easier, frankly. It lets us move things around. It lets us do tracing right on the diagram. It lets us put constraints on requirements to limit the scope to what we can actually build. It lets us derive new requirements or refine a requirement when that requirement has not enough information to actually build something from it. It also lets us clean up inconsistencies, and it helps bring them to light. Now, a lot of the systems that I work have literally thousands, if not tens of thousands of requirements. And it makes absolutely no sense at all to put all of those requirements on one diagram. I mean, even if we had a big plotter and used an F-size paper, we'd still have font down around 1 or 2 and we wouldn't be able to read anything. Secondly, the requirements diagram is really good for looking at requirements, but it doesn't replace a requirements management tool. So what's my suggestion? 1, have a requirements management tool, put your requirements in there, and have that as the master. 2, bring requirements in and put them on diagrams for what the work that you're doing is. So if I'm looking at a use case, I'll show the requirements that I trace to on that use case. If I am trying to understand how something works, or if I need to derive a new requirement, I can put it right there on the diagram that I'm dealing with. It may not have to be on a requirements diagram, but it might. Speaking of use cases, a use case diagram is something that a lot of us have seen. And by the way, use case is a terribly overused and overloaded term. Within the SysML, a use case is a feature or a function of the system. It is what the system is supposed to do, not how it's going to do it. So don't try to derive everything in there. As a matter of fact, for years I didn't find a lot of usability to a use case diagram. And then I heard someone say, hey, think of use cases as chapters of a book. And a use case diagram is a table of contents. So in this example, I've got provide user interface or control door locks. I can click on those and follow them down, but I know what the main features and functions of the system are. In addition to use cases themselves, there are a couple of really key things on the diagram. The first is those stick figures around the outside. Those are actors. Now, actors can represent a person, but they're more common in our world, represent another piece of hardware or another system or subsystem, something physical, but that's out there. Really, all an actor is something external to the system that we're building. The boundary box, in this case, the box that says Smart Home System, the boundary box defines the boundary of our system, or the piece of the system that we're looking at, or the piece of the subsystem that we're looking at, all the way down, you see. Basically, everything on the inside is what we're getting paid to build, or maybe what we're getting paid to build right now. Everything outside of it is stuff that is outside the system, and generally we're not going to model. Now, the interactions are the lines between the actors and the use cases. Those show that there is some interaction. We don't put an arrow on it to show which way it goes, because the forces can go, the forcing function, if you will, can go either in or out. And at this level, we don't care a whole lot. We will care later on. Right now, it's about showing that that interaction is there. Once we have the use case and we want to put more information about it, because let's be honest, control thermostat really doesn't tell you a whole lot. What we want to do is refine that use case. And there's a couple of different ways that we can refine it. The first way, and probably the most common, is with an activity diagram. Now, an activity diagram looks like a flowchart, and it's related, but it's more like a flowchart on steroids because it does a whole lot more. The activity diagram can do things like accept an event. That's what that little flag up in the upper left-hand corner is. Or it can send an event, the little arrows down in the two swim lanes pointing off to the right. It can send events to other things. In the meantime, it follows basic logic. And the key point of an action, the little rounded corner squares there, those are actions. They represent a unique step, if you will. And an action is something that can't be interrupted and ideally takes no time. So the action begins when the control flow, the arrow, the dashed arrow that's pointing to it, gets there and immediately continues, and you go on to the next one. Now, sometimes you'll see more than one arrow or more than one control flow pointing it in, or you may show both control and data coming in. I don't have any data on this one. If I have that, the action does not start executing until all of its inputs are met, with some special characteristics that we'll talk about in a later video when we get to more details. The key point, though, is activity diagrams are pretty understandable even by people who've had no training in them. As a matter of fact, on one program that I had with the United States Postal Service, I put together a bunch of activity diagrams, and I tried to document how we understood the system to work. I gave those activity diagrams to the guy who knew the most about the machine system that we were in the process of changing. And he looked at them and blessed most of them, but on at least one he looked at it and said, oh wait, we don't do this anymore and haven't done it in years. Well, by catching that, we saved expenses associated with hardware and software and testing, because it was stuff we didn't need to do that somebody checking was able to capture. So these are really easy to understand. And by the way, the guy who did that review, he was the chief technician and repair guy for that machine for the United States Postal Service. He had no training in systems engineering, in software engineering, and especially no training in SysML. Every pass through an activity diagram shows a sequence. And a sequence diagram is how we capture the sequences. Sequence diagram shows the calls that are being made from one part of the system to the next. These lifelines here going down from, for example, the dash line coming down from pump switch or from pressure sensor, those indicate the part of the system that we're looking at. And you can think of time as going down from the top to the bottom. The arrows that go across represent either synchronous or asynchronous calls. The line with an open arrowhead, EV power on, for example, that shows an asynchronous call. It happens at the call goes at the caller's context, but it's handled in the receiver's context. That's opposed to something like get pressure between the back pressure monitor and the pressure sensor. That is a synchronous call, and that happens at the caller's context, and the callee responds to it immediately. Again, we're going to have a whole other video on different ways and more detail about sequence diagram sequence, including what that box means and how the alternate paths or loops or reference paths, how all of those work. A state machine is something that most folks are familiar with. Basically, you're in one state until a very specific thing happens and you go to another state. The states can be nested and they can be deeply nested, but you're only in one set of states at a time. The state machine is a pattern, so your software guys should be implementing it as such. It helps make sure that the states get properly implemented and that you don't break something as you pull in and out of a state. I find that in the real-time embedded world, once we start using state machines, they become your go-to, because almost every program that I've worked has had states and modes of the system. The package diagram is the first of the structure diagrams that we're going to discuss. And a package diagram shows a way to arrange your work. It also shows dependencies. If you have a lot of dependencies between packages, especially one that go circular, A is dependent on B and B is dependent on A, that may be a place to look for potential conflicts and problems. The key structural diagrams that you'll spend almost all of your time with are the block definition diagram and the internal block diagram. These show the structure of the system, the larger pieces of the system. They show the relationships and the physical blocks themselves. Now, blocks have behavior. They have data that can be associated with them. We call those attributes. And they have operations that they can perform. All of that we'll get to when we talk about structural diagrams in the later section. An internal block diagram is the block definition diagram. We take the block for each of those and we refine, we break it up, we decompose it into its parts. Literally, that's what we call these. These parts are blocks, and these parts have multiplicity. That means if you need more than one, you show them on here. We also show the interfaces between the outside block and other blocks on this diagram. A special diagram that's used within SysML is the parametric diagram. Parametric diagrams are used to model the physical world and the dynamics of the physical world. They can be integrated with other tools. For example, a common one to use is Simulink, or they can execute on their own if your modeling tool supports execution, like IBM's Rhapsody does. These use attributes and they use constraints, and the constraints are typically your equations of motion or your dynamics that you're going to try to capture. You may not have noticed this, and I didn't call it out until now, but every one of the diagrams that I showed had a diagram frame, and it had this header at the top. This header serves a lot of purposes. For one thing, it helps you easily identify what you're looking at. But another thing is the boundary, the frame itself represents whatever that higher level thing is. So on a internal block diagram, the boundary, the frame, is the owning block. Or on an activity diagram that's being used to refine a use case, that boundary is the use case. It's a convenient notation. As I said, this was going to be just a quick overview. In the next video, we're going to show modeling requirements, and following that, you can see modeling use cases, refining the use cases, modeling structure, modeling behavior. So if you do have questions about the specifics, you can jump to those, but I would recommend seeing all of them first because it'll make things easier. And don't forget, while this set is done for systems engineers, I've got a companion set that is done for the software guys, and you may want to watch those too. If you've got any questions, feel free to reach out to me. I'm Jeff Cohen, that's Jeff at 321gang, or check out the company website, www.321gang.com. We offer sales and service, support, and consulting and training on modeling and lots of other products. Thanks.